Have you ever laid on a grassy field on a warm summer afternoon, feeling the sun's gentle heat on your skin? That comforting warmth we experience is just a tiny whisper of the universe's incredible thermal symphony. Out there, beyond our atmosphere, temperatures reach extremes so mind-boggling they challenge everything we know about physics and reality itself. Picture the surface of our sun, where temperatures soar to nearly 10,000 degrees Fahrenheit, hot enough to vaporize every known substance on Earth instantly. Now imagine temperatures so cold that atoms nearly stop moving altogether, where matter behaves in ways that seem to defy the very laws of nature. These aren't theoretical concepts, but actual conditions found throughout our cosmos, from the hearts of collapsing stars to the vast empty spaces between galaxies. What if I told you that the temperature range we're about to explore spans from negative 459.67 degrees Fahrenheit to over 18 billion degrees? These numbers are so extreme they barely register as meaningful concepts to our human experience. We're talking about environments where hydrogen fusion occurs naturally, where matter becomes so dense and hot that it transforms into entirely new states of existence, and where the cold is so absolute that quantum effects dominate reality. This isn't just about big numbers, it's about understanding the fundamental forces that shape our universe, from the birth of stars to the eventual heat death of everything. The thermal extremes we'll discover today reveal the universe's most dramatic processes, showing us where elements are forged, where space-time itself behaves strangely, and where the boundaries of physics are constantly being rewritten. Throughout this journey, we'll uncover 30 astonishing facts about these incredible temperatures, each one more mind-bending than the last. You'll learn why scientists create temperatures hotter than the sun's core right here on Earth, what happens to matter at temperatures approaching absolute zero, and how the vacuum of space can be both incredibly hot and unimaginably cold depending on where you look. We'll explore stellar nurseries where new stars are born in clouds of superheated gas, dive into the mysteries of neutron stars with surfaces hotter than most supernovas, and venture into the cosmic voids where temperatures drop to within fractions of a degree of the coldest possible temperature in the universe. This exploration will completely transform how you perceive the cosmos, revealing a universe of thermal wonders that simultaneously defies and defines our understanding of reality. While we often picture the cores of massive stars or the remnants of supernovas as the hottest places imaginable, the most extreme temperature ever recorded actually occurred in a laboratory right here on our own planet. In 2012, at the CERN laboratory in Switzerland, scientists using the Large Hadron Collider achieved something almost beyond comprehension. By smashing lead ions together at nearly the speed of light, they created a fleeting speck of matter heated to an astonishing 5.5 trillion degrees Celsius. To even begin to grasp that number, consider that the core of our sun, the powerhouse that fuels all life on Earth, burns at a comparatively cool 15 million degrees. The temperature achieved in that collider was over 366,000 times hotter. At that unimaginable heat, the very building blocks of matter break down completely. Protons and neutrons melt away, freeing the quarks and gluons that are normally locked inside them to create a primordial soup known as quark-gluon plasma. This isn't just a scientific curiosity, it's a recreation of the state of the entire universe mere microseconds after the Big Bang. For the tiniest fraction of a second, we weren't just observing the past, we were literally recreating it, offering a direct window into the conditions that gave birth to everything we know. This achievement demonstrates that the most extreme frontiers of temperature aren't always out in the distant cosmos. Sometimes they're being unlocked by human curiosity right here at home, pushing the boundaries of what we know about the fundamental nature of reality itself. Now let's turn our attention from that record-breaking laboratory creation to the star that makes our very existence possible. While it might not hold the title for absolute hottest place, our Sun's core operates at a temperature that is still almost beyond human comprehension. At 15 million degrees Celsius or 27 million degrees Fahrenheit, the Sun's center functions as the ultimate nuclear furnace. This isn't just heat generated by simple combustion like a fire on Earth. This is the result of one of the universe's most fundamental and powerful processes. Under the crushing weight of the Sun's own immense gravity, hydrogen atoms are forced together with such incredible pressure and temperature that they overcome their natural repulsion and fuse into helium. This process of nuclear fusion releases staggering amounts of energy in the form of light and heat, the very same energy that has powered life on our planet for billions of years. The efficiency of this stellar engine is almost difficult to believe. Every single second, the Sun converts approximately 4 million tons of its mass directly into pure energy. To put that into perspective, that's the equivalent mass of a small mountain transformed into energy in the blink of an eye. And this process has been continuing relentlessly for over 4.5 billion years. What's truly remarkable is how this incredible release of energy is contained and regulated. The Sun's enormous gravitational force creates a perfect balance, pressing inward with just enough strength to contain the ferocious nuclear reactions trying to explode outward. This delicate equilibrium between gravity and radiation pressure is what allows our Sun to burn steadily rather than detonating like a cosmic bomb. Perhaps the most astonishing aspect of the Sun's inner workings involves the journey of the light itself. Those photons generated deep within the core don't simply zip straight out to the surface. Instead, they embark on an epic 100,000-year odyssey, constantly being absorbed and re-emitted by the dense plasma as they slowly make their way outward. The sunlight that gently warms your skin today began its journey from the core long before human civilization even existed. This incredible timescale reminds us that the warmth we feel connects us directly to processes occurring deep within our star, making every sunbeam a messenger from the heart of a nuclear furnace that has sustained life on Earth since its very beginning. While our Sun's surface simmers at around 5,500 degrees Celsius, here on Earth we regularly witness a natural phenomenon that makes even that staggering heat seem almost mild by comparison. A typical lightning bolt during a thunderstorm superheats the air around it to a mind-numbing 30,000 degrees Celsius, that's 54,000 degrees Fahrenheit. This means the very air you're breathing during a storm can momentarily become 5 times hotter than the surface of the star that powers our entire solar system. This incredible temperature spike doesn't last long, typically only microseconds, but in that brief window it unleashes enough energy to fundamentally transform matter. What's truly fascinating is how this extreme heat is generated. Unlike the sustained nuclear fusion in the Sun, a lightning bolt's heat comes from the immense electrical resistance of the air itself. As the electrical charge builds between clouds or between a cloud and the ground, the voltage eventually becomes so great that it overcomes the air's insulating properties. When that happens, electrons surge through the atmosphere, colliding with air molecules with such force that they're literally torn apart. This violent process creates a superheated plasma channel, the visible lightning bolt we see, where temperatures instantly skyrocket to those 30,000 degrees. The air molecules can't handle this sudden energy input and expand explosively, actually moving faster than the speed of sound and creating the shockwave we perceive as thunder. Perhaps the most dramatic demonstration of this incredible heat is what happens when lightning strikes sandy ground. The instantaneous temperature is so extreme that it can vaporize silica sand instantly, fusing it into bizarre, glassy structures called fulgurites. These fossilized lightning formations preserve the exact path the bolt took through the ground, creating beautiful, branching sculptures of natural glass. Each fulgurite is a permanent record of that momentary encounter with one of nature's most powerful forces. transforming ordinary sand into something extraordinary through heat that rivals anything our sun can produce at its surface. Just when you thought space couldn't get any more extreme, we journey from the brief, searing heat of a lightning bolt to the profound, eternal chill of the Boomerang Nebula. Located 5,000 light-years away in the constellation Centaurus, this beautiful, bow-tie-shaped cloud of gas holds a record that stands in stark contrast to everything we've explored so far. It is officially the coldest known natural place in the entire universe. We're not just talking about a little bit chilly. The temperature here plummets to a mere 1 Kelvin. That is negative 272.15 degrees Celsius, or a mind-numbing negative 457.87 degrees Fahrenheit. This places it within a single, fragile degree of absolute zero, the theoretical temperature where all atomic motion would cease entirely. What makes this place so incredibly cold? The answer lies in the dramatic death throes of the star at its heart. This isn't a young, vibrant star, but an old, dying red giant in its final stages of life. In a last gasp of cosmic effort, this star is expelling its outer layers of gas at a staggering speed over 164 kilometers per second. That's 10 times faster than the speed of sound here on Earth. This supersonic eruption acts like a cosmic air conditioner. As the gas expands into the vacuum of space at such tremendous velocity, it cools down precipitously, in much the same way that the gas expanding in your refrigerator's coils draws heat away from your food. The nebula is essentially a natural, interstellar cooling system operating on a monumental scale. To truly appreciate how cold 1 Kelvin is, we need a point of comparison, and the universe provides a fascinating one. The entire cosmos is bathed in the faint, leftover warmth from the Big Bang itself, known as the cosmic microwave background radiation. This ancient afterglow has cooled over billions of years, but it still registers at a balmy 2.7 Kelvin. This means the Boomerang Nebula is significantly colder than the deepest, emptiest voids of space between galaxies. It's actively cooling itself below the universe's baseline temperature, a feat that makes it an incredible cosmic anomaly. This nebula shows us that even in the vastness of space, nature can create pockets of extreme conditions that defy the ambient environment, presenting us with a profound and beautiful mystery that continues to captivate astronomers. From the profound cosmic chill of the Boomerang Nebula, we arrive at the ultimate benchmark for cold itself. Absolute zero, measured as 0 on the Kelvin scale, represents the theoretical point where all atomic motion grinds to a complete and total halt. This isn't just very cold, it is the foundational baseline of temperature in our universe, the absolute bottom. To put it in more familiar terms, that's negative 273.15 degrees Celsius, or an almost unimaginable negative 459.67 degrees Fahrenheit. This temperature isn't just a number on a chart, it represents a fundamental limit imposed by the very laws of physics. According to the third law of thermodynamics, it is physically impossible for any system to actually reach absolute zero. You can get closer and closer, but you can never quite arrive, making it a perpetual goal for scientists pushing the boundaries of low-temperature physics. And push those boundaries they have. In laboratories around the world, physicists have performed miracles of cooling, creating isolated pockets of matter that are within a few billionths of a degree of this ultimate cold. To achieve this, they use incredibly sophisticated methods like laser cooling and magnetic evaporation, techniques that carefully strip away the tiniest amounts of energy from atoms. These aren't your everyday freezers, they are complex scientific instruments designed to create some of the most unique conditions found anywhere. At these infinitesimally small fractions of a degree above absolute zero, the normal rules of physics that govern our everyday world begin to break down, and the bizarre, counterintuitive rules of quantum mechanics take over. Matter starts to behave in ways that seem like they're from a science fiction novel. One of the most spectacular of these quantum behaviors is a state known as a Bose-Einstein condensate. In this state, a cloud of atoms cooled to near absolute zero collapses into a single, unified quantum entity. It's as if the thousands of individual atoms lose their personal identities and begin to act as one single superatom, a phenomenon that can only be described with quantum physics. Another incredible effect is superconductivity, where certain materials, when chilled to these extreme temperatures, suddenly lose all electrical resistance. This means an electric current could flow through a superconducting loop theoretically forever without any loss of power, a property with revolutionary potential for technology and energy transmission. Perhaps the most visually strange behavior is superfluidity. When liquid helium is cooled to around 2 Kelvin, it transforms into a superfluid. This substance has zero viscosity, meaning it can flow without any friction whatsoever. A superfluid can defy gravity, creeping up and over the walls of its container in a thin film, and it can even form a perpetual fountain that never stops. These aren't laboratory tricks, they are profound demonstrations of the quantum world, a realm normally hidden from view that only reveals its true nature under the most extreme conditions imaginable. Leaving behind the theoretical extremes of absolute zero, we arrive at a world where theory becomes a crushing, melting reality. While Mercury may orbit closer to the Sun, the title for the hottest planet in our solar system belongs to Venus, a world that has perfected the art of turning up the heat to truly apocalyptic levels. Its surface temperature is a constant 465 degrees Celsius, or 869 degrees Fahrenheit, hot enough to not just melt lead, but to keep it in a permanent, shimmering puddle. This isn't a dry heat or a seasonal spike. It is a global, unending inferno that makes the surface of Mercury seem temperate by comparison. So how does a planet that receives less solar energy than its neighbor become such a furnace? The answer lies not in its proximity to the Sun, but in its atmosphere. Venus is shrouded in an incredibly thick, toxic blanket of air composed of 96% carbon dioxide. This dense atmosphere has triggered what scientists call a runaway greenhouse effect. Sunlight passes through the clouds and warms the surface, but when that heat tries to radiate back out into space as infrared radiation, the CO2 molecules trap it with terrifying efficiency. The heat builds up relentlessly with nowhere to go, turning the entire planet into a pressure cooker that has been simmering for billions of years. It's a stark and sobering lesson in how a planet's atmosphere, not its distance from its star, ultimately controls its climate. The horror of Venus doesn't stop at the heat, however. The atmospheric pressure at the surface is a crushing 92 times greater than what we experience here on Earth. To a human, it would feel equivalent to being nearly a kilometer deep in the ocean. The clouds themselves offer no respite, as they are not made of water vapor but of corrosive sulfuric acid, raining a burning, toxic drizzle that evaporates before it even hits the scorching ground below. This combination of immense pressure, searing heat, and acidic air creates what is arguably the most hostile surface environment in our entire solar system. Our attempts to explore this hellscape read like a chronicle of cosmic bravery. The Soviet Union's Venera landers are the only spacecraft to have ever sent back images and data from the surface. These robust probes were engineering marvels designed to withstand the unimaginable. Yet, even they could only survive for mere minutes, the longest enduring just 127, before being simultaneously crushed, melted, and corroded into silence, their final transmissions painting a picture of a stark, desolate, and truly alien world. Venus stands as a permanent reminder that a planet's environment is a delicate balance, and a warning of how easily a world can transform into an uninhabitable nightmare. While we've been exploring the most extreme and violent temperatures across the cosmos, it's easy to overlook the most universal and constant thermal blanket that envelops everything, the cosmic microwave background. This isn't the heat of a star or the chill of a nebula. It's the faint, lingering warmth from the birth of the universe itself, a thermal echo of the Big Bang that has been steadily cooling for over 13 billion years. Today, it registers at a remarkably even 2.725 Kelvin, which is just 2.725 degrees above absolute zero. In more familiar terms, that's negative 270.4 degrees Celsius, or an almost unimaginable negative 454.7 degrees Fahrenheit. This isn't a temperature you find in one specific location. It is everywhere, in every direction, permeating the entirety of space. If you could see microwave radiation with your eyes, the entire night sky wouldn't be black at all. It would glow with a uniform, ethereal light. The story of this light is the universe's own origin story. For the first 380,000 years after the Big Bang, the cosmos was an opaque, searing hot fog of plasma, too dense for light to travel any meaningful distance. Photons were constantly bouncing off free electrons, trapped in a chaotic, superheated soup. But as the universe expanded and cooled, it eventually reached a critical temperature around 3000 Kelvin, where electrons could finally combine with protons to form the first stable hydrogen atoms. In this moment, known as recombination, the fog suddenly cleared. The universe became transparent, and that trapped light was finally set free on a journey that continues to this day. The light we now detect as the cosmic microwave background is that very first flash, a baby picture of the infant universe, stretched and cooled by the unimaginable expansion of space itself over billions of years. What makes this ancient glow so crucial to science are the tiny imperfections hidden within its incredible uniformity. When we build exquisitely sensitive instruments like the Planck Space Observatory to map this background radiation, we don't see a perfectly smooth temperature. Instead, we find minuscule fluctuations, tiny variations on the order of mere millionths of a degree. These tiny ripples in temperature are the most important fingerprints in all of cosmology. They represent the slight variations in density in that early universe, the gravitational seeds from which everything we see today eventually grew. The slightly denser, slightly warmer spots held the gravitational potential that, over eons, pulled in matter to form the first stars, the galaxies, the immense clusters of galaxies, and the vast cosmic web that structures the modern universe. Without these infinitesimal temperature differences imprinted on the cosmic background, the universe would be a featureless, uniform void. We are literally seeing the blueprint for all cosmic structure. This incredible discovery didn't just provide the smoking gun evidence for the Big Bang theory. It gave us a precise recipe for our universe, allowing us to calculate its age, composition, and geometry with astounding accuracy, all from reading the subtle temperature variations in the oldest light there is. But if you think the temperatures we've encountered so far are extreme, prepare to meet the universe's ultimate pressure cookers. When the largest stars, those at least 8 times more massive than our Sun, reach the end of their lives, they don't fade away quietly. They die in the most violent explosions known to science, supernovas, and from that unimaginable cosmic detonation, a new and even more bizarre object is born. The outer layers of the star are blasted into space, but the core, no longer supported by nuclear fusion, collapses under its own immense gravity. What remains is a neutron star, an object that packs more mass than our entire Sun into a sphere no wider than a city. This creates density so incomprehensible that a single sugar cube-sized piece of this material would weigh 1 billion tons here on Earth. The forces at play during this birth are so titanic that they forge an object which is quite literally a newborn inferno. Fresh from the supernova furnace, the surface of a neutron star simmers at around 1 million Kelvin. To put that into perspective, that's nearly 200 times hotter than the surface of our Sun. This extraordinary heat makes these city-sized objects glow with an intensity that peaks not in visible light, but in the high-energy realm of X-rays. If our eyes could see X-rays, the night sky would be dotted with these brilliant, piercing beacons. Yet, as extreme as the surface is, it's merely the lukewarm crust hiding a far more ferocious interior. The true thermal monster lies deep within its core. The core of a neutron star is where physics reaches its absolute breaking point. Here, temperatures are thought to soar to over 1 trillion Kelvin. This staggering heat is generated by the very process that gives these stars their name. Under the unimaginable pressure of the collapse, electrons are literally forced into protons, their opposite charges cancelling out to form neutrons. This transformation releases a torrent of energy in the form of neutrinos, which carry away tremendous heat, and it's this process that superheats the core to those trillion-degree temperatures. At this level of heat and density, matter ceases to behave in any recognizable way. Protons and neutrons themselves may break down into a swirling soup of their constituent quarks, creating states of matter that cannot be replicated anywhere else in the universe. A neutron star is therefore much more than just a remnant. It is a continuous cosmic laboratory, a place where the fundamental rules of nature are written in extremes of temperature and density that defy human comprehension. After exploring the unimaginable heat of a neutron star's core, we turn to a concept that seems far simpler but is often deeply misunderstood: the temperature of space itself. We often hear space described as a cold, empty void, but this common phrase hides a much more complex and fascinating reality. The truth is, the vacuum of space doesn't have a temperature in the way that air or water does. Temperature, by definition, is a measure of the average kinetic energy of particles in a substance. But in the near-perfect vacuum between celestial bodies, there are so few particles that the concept of an ambient temperature almost loses its meaning. An astronaut floating in the void wouldn't instantly feel cold in the way we experience it on Earth. Instead, they would face a far more subtle and dangerous thermal challenge. The real story of temperature in space is not about the environment itself, but about what happens to any object placed within it. Without an atmosphere to conduct heat away, an object in space can only lose energy through one primary method: radiation. Every object slowly emits infrared radiation, and over an incredibly long time, this process would allow it to radiate all its heat away into the vastness, eventually approaching the frigid temperature of the cosmic microwave background. But this is only half the equation. While an object is constantly radiating heat away, it is also absorbing energy from every radiant source around it, most significantly from the sun. This creates a dramatic and potentially deadly balancing act. The actual temperature an object reaches depends entirely on its exposure to these energy sources and its own ability to absorb or reflect that energy. This leads to the most extreme temperature swings imaginable. Consider an astronaut on a spacewalk outside the International Space Station. The side of their suit facing the sun is being bombarded by the full, unfiltered intensity of solar radiation. With no atmosphere to scatter or absorb the light, the sun's rays hit with their maximum force, rapidly heating that side to a blistering 120 degrees Celsius, hot enough to boil water. Meanwhile, the side of the suit in shadow is only exposed to the deep cold of empty space, and it can plunge to a bone-shattering negative 157 degrees Celsius. An astronaut literally exists between the conditions of a blazing oven and a cryogenic freezer, all at the same time. This is why every single spacecraft, satellite, and spacesuit is equipped with incredibly sophisticated thermal control systems. They use a combination of highly reflective white coatings or mirrors to reject solar heat, layers of gold-colored insulation to retain internal warmth, and heat-radiating panels that act like car radiators to dump excess internal heat generated by electronics into space. Managing these wild temperature fluctuations isn't just a matter of comfort. It is absolutely critical for the survival of both human astronauts and the sensitive electronics that keep them alive. making thermal engineers some of the most vital unsung heroes of space exploration. From these extreme temperature swings experienced by objects in space, we now turn our attention to a cosmic phenomenon that exists in a perpetual state of thermal identity crisis. Brown dwarfs are the universe's failed stars, celestial objects caught in a perpetual twilight between planet and star. They form in the same way stars do, from collapsing clouds of gas and dust, but they simply don't have enough mass to cross the critical threshold. To ignite the sustained hydrogen fusion that defines a true star, an object needs to compress its core to about 3 million Kelvin, a feat that requires at least 75 times the mass of Jupiter. Brown dwarfs fall short with masses between about 13 and 75 Jupiters. They're born with tremendous internal heat, often reaching millions of degrees in their cores from the gravitational energy of their formation, but without a central nuclear furnace to keep them stoked. Their story is one of inevitable and permanent cooling. What makes these objects so fascinating is their long, slow fade into obscurity. A young, hot brown dwarf might have a surface temperature similar to a low-mass star, around 2,800 degrees Celsius, glowing a dim red. But as billions of years pass, this heat steadily radiates away into space. They cool down through their spectral classes from red to a faint magenta, and eventually into the infrared, becoming invisible to the human eye. The coolest known brown dwarfs, like WISE 0855-0714, have reached atmospheric temperatures that are startlingly familiar to us. This particular dwarf, located just 7.2 light-years away, registers at a mere -23 to -13 degrees Celsius. That's right, the surface temperature of this cosmic object is comparable to a cold winter day here on Earth. This leads to one of the most incredible possibilities in all of astronomy. At these Earth-like temperatures, the physics of their atmospheres suggests that brown dwarfs could actually have weather. Not the scorching silicate or iron rain of hotter dwarfs, but something far more recognizable. Scientists theorize that the coolest, oldest brown dwarfs might possess water vapor clouds in their upper atmospheres. The conditions could be just right for the formation of water droplets or even snow, composed of water ice swirling in alien skies. This incredible notion completely blurs the line we try to draw between planets and stars. We have a substellar object born like a star, massive enough to briefly fuse deuterium or lithium in its youth, yet now cool enough to potentially host a type of weather we experience on our own planet. A brown dwarf is a living thermal timeline, a cosmic remnant that showcases the slow, relentless victory of entropy over the fierce heat of creation, ultimately becoming a cold, dark witness to the passage of eons in the silent depths of space. Yet even these dramatic swings we see in Earth orbit are nothing compared to the ultimate solar system champion of temperature extremes, a world that takes this concept to its absolute limit. Mercury, the solar system's innermost planet, experiences temperature variations so severe they are almost impossible to fully comprehend. Because it possesses virtually no atmosphere, just a scant trace of gases, it has no protective blanket to trap heat or distribute warmth around the planet. This lack of an atmosphere, combined with its incredibly long day, creates a world of two brutally divided halves. The side facing the sun bakes relentlessly under the unfiltered glare for 59 consecutive Earth days, with surface temperatures soaring to a blistering 430 degrees Celsius. That is hot enough to melt lead and even zinc into shimmering metallic puddles. Meanwhile, the side turned away from the sun is plunged into a deep freeze that lasts an equally long 59 Earth day night, where temperatures can plummet to a cryogenic -180 degrees Celsius. This difference of over 600 degrees Celsius between day and night isn't just a record. It represents the most extreme thermal swing of any planet or moon we've discovered. To put that into a more human perspective, that's the equivalent of experiencing the surface temperature of a commercial pizza oven and then, in the very same location just a few weeks later, the cold of a laboratory cryofreezer. This perpetual cycle of extreme thermal stress has profound effects on the planet's very geology. The rocks on Mercury's surface are subjected to a constant process of expansion and contraction on a massive scale, a phenomenon that likely contributes to the planet's heavily cracked and scarred landscape. This is a world where the ground itself is quite literally being pulled apart and pushed back together by the sheer force of temperature change over million-year timescales. What's perhaps most fascinating is that despite being the closest planet to the Sun, Mercury is not actually the hottest. That title, as we know, belongs to Venus and its runaway greenhouse effect. Mercury's lesson is a different one. It demonstrates with stunning clarity that a planet's atmosphere is its primary climate control system. Without one, a world is completely at the mercy of its star, subjected to the raw, unmoderated power of solar radiation. This makes Mercury a perfect natural laboratory for studying the effects of solar wind and radiation on airless bodies, giving us crucial insights into the history of our own moon and asteroids. Its extreme environment stands as a stark monument to the power of a star and the critical importance of having just the right blanket of air to create a stable, habitable world. While we marvel at the temperatures achieved in our laboratories or locked within our solar system, the true masters of stellar heat reveal themselves not in fiery reds or yellows, but in a brilliant, searing blue. This brings us to a fundamental and beautiful rule of the cosmos. A star's color is not merely an aesthetic quality, it is a direct and precise thermometer. The entire sequence, from cool red to warm yellow to hot white, culminates in the most extreme stellar furnaces of all, which radiate an intense violet-tinged blue. At the very pinnacle of this temperature scale are the blue hypergiants and the enigmatic Wolf-Rayet stars, celestial leviathans that make our Sun seem like a faint, cool ember in comparison. The surface temperatures of these stellar behemoths are almost beyond comprehension. While our Sun's surface simmers at around 5,800 Kelvin, a typical blue hypergiant like Eta Carinii burns at a staggering 40,000 Kelvin. But even that is merely the beginning. Wolf-Rayet stars, the exposed, dying cores of massive stars that have blown away their outer hydrogen envelopes, push this thermal extreme even further. Their surfaces can reach an astonishing 200,000 Kelvin. To put that into a human context, if you could somehow place a tiny speck of material from such a star here on Earth, the sheer thermal radiation blasting from it would be instantly lethal from hundreds of kilometers away. Their energy output is so colossal that a single one of these stars can outshine entire galaxies of smaller, cooler stars. This incredible heat dictates a ferociously short and dramatic life cycle. These stars are the cosmic equivalent of brilliant fireworks, spectacular but fleeting. They are so massive and burn their nuclear fuel with such reckless abandon that they exhaust their hydrogen, then helium, and begin fusing ever heavier elements in a desperate race against gravity. This prodigious fuel consumption means their lifetimes are measured in just a few million years, a mere blink in cosmic time compared to the 10 billion-year lifespan of a star like our Sun. Their inevitable fate is to die in some of the most violent explosions in the universe, supernova or even hypernova, which can leave behind black holes and seed the galaxy with the heavy elements forged in their brief, incandescent lives. Perhaps their most profound impact, however, is on the space around them. These stars are relentless engines of ultraviolet radiation. Their intense light doesn't just illuminate nearby gas clouds, it violently energizes them, stripping electrons from atoms in a process called ionization. This sculpts and lights up vast nebulae, creating some of the most beautiful and complex structures observed in space, like the iconic pillars of creation in the Eagle Nebula. In these stellar nurseries, the very same radiation that tears molecules apart also provides the energy that triggers the collapse of new gas clouds, catalyzing the birth of the next generation of stars. Thus, these hottest, bluest stars are not just agents of destruction, they are also cosmic architects, their immense heat writing the recipe for star formation and ultimately for the creation of the elements necessary for planets and life itself. Yet even the most terrifying volcanic eruptions on Earth, with rivers of rock glowing at 1200 degrees Celsius, are a gentle warmth compared to the true thermal monsters that inhabit the cosmos. Our planet's lava represents the absolute upper limit of natural heat on the surface, a force capable of obliterating everything in its path. But when we place it on the universal temperature scale, it barely registers. The 15 million degree core of our Sun isn't just a little hotter. It is over 12,000 times more intense. This difference isn't merely quantitative. It represents a fundamental shift in the nature of matter and energy. Lava is molten rock, a state we can comprehend and even replicate. The core of a star, however, is a plasma where atoms are stripped bare and nuclear fusion generates energies that operate on an entirely different physical plane. To truly grasp this chasm in scale, we can use a simple but powerful analogy. Imagine the heat from a single, small candle flame. That gentle warmth is roughly equivalent to the searing heat of a lava flow when compared to the Sun's interior. Just as you wouldn't use a candle to heat an entire building, the energy in lava is insignificant next to the cosmic engine of a star. This staggering disparity exists because these temperatures are generated by completely different processes. Volcanic heat comes from the radioactive decay of elements deep within the Earth's mantle and the immense pressure of the planet's interior. It is a geological phenomenon. Stellar heat, by contrast, is the product of nuclear physics, where mass is directly converted into energy following Einstein's famous equation. This is why the most violent volcanic event in Earth's history is a quiet whisper next to the continuous, universe-shaping roar of a star. This perspective doesn't diminish the raw power of our planet's volcanism. Instead, it magnifies our awe for the universe. It establishes a new benchmark for what extreme truly means. Our hottest laboratory experiments, our most furious natural disasters, all reside on the lower end of the cosmic thermal spectrum. This fact is a profound humbler, reminding us that the conditions we consider unimaginably violent on our planet are just the baseline normal for the universe at large. The same physical laws that govern a bubbling lava lake also govern a supernova, but the scales of energy involved are so vastly different that they create realities we can scarcely dream of, let alone experience. But this journey into extreme cold isn't confined to distant nebulae. We can find pockets of profound chill right in our own celestial backyard on the surface of our own moon. Tucked away in the deepest craters at the lunar South Pole are places of eternal night, shadows that have not been touched by a single ray of sunlight for over 2 billion years. These are the solar system's ultimate cold traps, and the temperatures they achieve are almost unreal. NASA, a lunar reconnaissance orbiter, has measured the floors of these abyssal craters, like Shackleton and Faustini, at a staggering negative 247 degrees Celsius. That is a mere 26 degrees above the absolute bottom of the temperature scale, making them some of the coldest known places in our entire solar system. The physics behind this deep freeze is both simple and profound. Because the moon has virtually no axial tilt and only a very thin wisp of an exosphere, there is no atmospheric blanket to distribute heat. In these permanently shadowed regions, any heat that was ever there has simply radiated away into the blackness of space over eons, with no new energy coming in to replace it. They have been sitting in a state of perfect, frozen equilibrium for longer than multicellular life has existed on Earth. These are not just cold places, they are natural deep freeze archives, preserving a record of events that occurred in the early solar system. And it is within these ultra-cold, pristine environments that scientists have made one of the most exciting discoveries in modern planetary science: vast deposits of water ice. The cold is so intense and so constant that any volatile material, like water molecules delivered by comet impacts over billions of years, that stumbles into these craters becomes permanently trapped. It flash freezes onto the soil and cannot escape, collecting in layers that could be dozens of feet thick. This ice is not like a glacier on Earth, constantly changing and moving. It is a historical ledger, a frozen time capsule that may contain clues about the origin of Earth's water and the composition of the ancient comets that once bombarded the inner solar system. This transforms these desolate, frigid craters from mere curiosities into some of the most scientifically valuable real estate in the entire solar system. For future explorers, this water is the key to sustainable lunar habitation. It can be mined and split into hydrogen and oxygen for rocket fuel, turning the moon into a cosmic gas station for missions venturing deeper into space, or it can be purified for drinking and growing plants. But perhaps more importantly for scientists, it is an untouched record, a frozen library holding volumes of information about the history of our cosmic neighborhood, waiting in the perfect cold to tell its story. But all of these stellar and planetary extremes are merely the steady-state operations of the cosmos. To witness the universe's most concentrated and catastrophic release of thermal energy, we must witness the spectacular death of a star. A supernova is not just an explosion, it is the ultimate cosmic blowtorch, a brief, universe-altering event where temperatures reach heights so absurd they challenge the very definitions of physics. While the core of a living star simmers at 15 million degrees, the heart of a supernova during its final collapse transcends that completely. In a fleeting moment measured in seconds, the temperature within that collapsing core skyrockets to over 100 billion Kelvin. This isn't just hotter than anything we've discussed. It is a thermal regime where matter and energy behave in ways we can only theorize about. This unimaginable heat is the direct result of the star's catastrophic gravitational collapse. After burning through its nuclear fuel, the star's core can no longer support its own immense weight. It implodes at nearly a quarter the speed of light, and all that gravitational potential energy is converted instantaneously into thermal energy. The force of this collapse is so violent that it doesn't just squeeze atoms together. It smashes atomic nuclei with such ferocity that they fuse into elements far heavier than iron in a process known as explosive nucleosynthesis. In this stellar forge, lasting only moments, the universe creates the entire periodic table's worth of heavy elements. The gold in your jewelry, the silver in electronics, the uranium that powers reactors. All of it was forged in these few seconds of apocalyptic heat before being blasted out across the galaxy by the ensuing shockwave. And that shockwave itself is a traveling inferno. As the rebound from the core collapse propagates outward at tens of thousands of kilometers per second, it superheats the star's outer layers to millions of degrees, tearing the star apart and ejecting its newly enriched guts into interstellar space. This expanding cloud of stellar material, now called a supernova remnant, continues to glow with intense heat for millennia. For thousands of years, these beautiful, intricate nebulae like the Crab Nebula emit most of their light not in the visible spectrum, but in high-energy X-rays, a testament to the searing temperatures within the expanding gas cloud. This persistent, high-energy glow is the long, slow cooling of a cosmic fireball, a permanent monument to a brief flash of heat so intense that it literally seeds the galaxy with the building blocks for new planets and ultimately for life itself. Leaving behind the cryogenic craters of our moon, we venture outward to the solar system's enigmatic frontier, where two distant giants present a fascinating thermal paradox. Uranus and Neptune, the so-called ice giants, hold court in the deep freeze of the outer solar system, where the sun is little more than a bright star. At their cloud tops, the temperatures are profoundly cold, even by cosmic standards. Uranus registers at a biting negative 214 degrees Celsius, while Neptune is just a touch colder at negative 218. These are not the absolute coldest temperatures we've encountered, but they are certainly among the most consistently frigid environments for a planetary surface in our celestial neighborhood. The sheer distance from the Sun means these worlds receive only a tiny fraction of the solar energy that warms the inner planets, plunging their outer atmospheres into a perpetual deep chill. But their name, ice giant, is one of the most brilliantly misleading terms in all of astronomy. It conjures images of frozen, solid worlds like colossal snowballs drifting in space. The reality is far more strange and wonderful. Their ice refers not to their surface condition, but to the chemical composition of their vast mantles. Beneath thick outer atmospheres of hydrogen and helium lies an enormous ocean. But this is no ocean of liquid water as we know it. It is a superheated, dense, and electrically conductive fluid composed of water, ammonia, and methane. Under the crushing pressure of thousands of kilometers of overlying atmosphere, these familiar substances are compressed into an exotic state of matter known as a supercritical fluid, which exhibits properties of both a liquid and a gas. This mantle is likely scorching hot, with temperatures estimated to reach several thousand degrees Celsius. So, we have a planet with a frozen, windy atmosphere that gives way to a searingly hot, slushy interior ocean, a true world of thermodynamic contradiction. The greatest mystery and source of heat, however, lies even deeper. At the very heart of each ice giant, scientists believe there is a core of rocky material and metals, perhaps comparable in mass to our entire Earth. The temperatures here are thought to be staggering, potentially rivaling the surface of the Sun at thousands of degrees. Yet, paradoxically, this material is not molten. The reason is the unimaginable pressure, millions of times greater than the pressure we experience at sea level on Earth. This incredible force keeps the rock in a solid state despite the extreme heat, defying our everyday experience where heat melts solids. This internal furnace is the engine of these planets' dynamic weather. While Uranus seems to have a relatively quiet interior, Neptune radiates more than twice the heat it receives from the Sun. This internal energy, left over from the planet's formation billions of years ago, is what fuels the fastest winds in the solar system, whipping frozen methane clouds across its blue atmosphere at speeds exceeding 2,000 kilometers per hour. These distant, icy worlds are therefore not the frozen, dead relics they might appear, but complex and dynamic planets, where the interplay between unimaginable pressure and intense internal heat creates some of the most unique and active environments in our entire solar system. While we've looked at cosmic temperatures from the cold depths of space to the hearts of dying stars, one of the most perplexing thermal mysteries has been sitting right in front of us all along, visible during every total solar eclipse. It involves our own Sun and a paradox that defies basic intuition. Logic would suggest that the farther you get from a heat source, the cooler things become. The Sun's visible surface, the photosphere, simmers at a toasty 5,500 degrees Celsius. Yet, if you travel outward from that surface into the Sun's outer atmosphere, called the corona, the temperature doesn't drop. It skyrockets, soaring to an incredible 1 to 2 million degrees Celsius. This is the coronal heating problem, a question that has baffled solar physicists for decades. How can the Sun's atmosphere be hundreds of times hotter than its surface? It would be like walking away from a campfire and suddenly feeling an overwhelming, blistering heat instead of a comforting warmth. This apparent violation of the laws of thermodynamics has been one of the most enduring puzzles in all of astronomy. To solve this mystery, we needed to go there. And that is precisely the monumental mission of NASA Parker Solar Probe, a spacecraft of almost unbelievable ambition and engineering. Its goal is nothing less than to touch the Sun by flying through this superheated corona itself. To do this, it must become the fastest human-made object in history, and more importantly, it must survive an environment that would vaporize any other spacecraft instantly. During its closest approaches, the probe experiences intense solar radiation that heats its front-facing surface to nearly 1,400 degrees Celsius. That's hot enough to melt iron and turn granite into lava. Yet, tucked safely behind its revolutionary thermal protection system, the probe's sensitive instruments enjoy a balmy room temperature around 30 degrees Celsius. This heat shield is a modern marvel. It's a lightweight carbon composite foam sandwich that's 97% air, only about 4.5 inches thick. One side is coated with a specially formulated white ceramic paint to reflect as much of the sun's energy as possible. The key to its success is not that it doesn't get hot, the sun-facing side glows a blinding red hot, but that it is an incredible insulator, preventing that intense heat from conducting through to the spacecraft body. The shield is so effective that the instruments huddled behind it are actually kept warm by their own electronics, requiring small heaters to keep them from getting too cold. It is a perfect, life-preserving cocoon, allowing the probe to sample the solar corona itself, and the data it is sending back is already revolutionizing our understanding of our star. The probe has flown through the birthplace of the solar wind, identifying where it transitions from a turbulent flow to a supersonic river of charged particles. It has captured the first ever measurements of the dust-free zone around the Sun, a region where intense heat is thought to vaporize interstellar dust into gas. Most critically, it has provided stunning evidence for what might be solving the coronal heating mystery. The data strongly suggests that the immense heat is generated by the constant, chaotic reconnection of the Sun's magnetic field lines. Think of the magnetic field as a vast web of rubber bands stretching across the solar surface. The churning plasma of the Sun is constantly twisting and tangling these lines. When they become too strained, they snap and reconnect in a new configuration, releasing enormous bursts of energy in the form of heat and accelerating particles. This process, called nanoflares, happens millions of times per second across the Sun, collectively turning the corona into a multi-million-degree oven. The Parker Solar Probe is not just exploring the Sun, it is uncovering the fundamental physics of how stars interact with their environment and how they shape the very space around them. While the cosmic stage is dominated by the violent, explosive heat of stellar furnaces, some of the most profound discoveries about our universe are being made in laboratories that pursue the opposite extreme, creating conditions of cold so absolute they defy our everyday understanding of reality. Scientists have used intricate combinations of laser beams and magnetic fields to achieve a feat that seems almost impossible. They have cooled clouds of atoms to within a billionth of a degree of absolute zero. To grasp the scale of this achievement, consider that the depths of interstellar space are a relatively warm 3 Kelvin. The Bose-Einstein condensate exists at a temperature of just a few nanokelvin, making it orders of magnitude colder than even the Boomerang Nebula, the coldest known natural place in the universe. This isn't just a record-breaking stunt, it is the creation of an entirely new state of matter, one that only reveals itself under these most extreme conditions. At these nanokelvin temperatures, something truly magical happens to matter. The individual atoms, now moving incredibly slowly, begin to lose their distinct identities. Their quantum mechanical wave functions, which normally define the probability of where each atom might be, begin to overlap and merge. What was once a cloud of separate particles collapses into a single, giant quantum entity, a superatom that behaves as one coherent wave. This is the Bose-Einstein condensate, a state of matter predicted by Satyendra Nath Bose and Albert Einstein nearly a century ago, but only first created in a lab in 1995, an achievement that later earned the Nobel Prize. In this bizarre state, the weird laws of quantum mechanics, which usually only operate on the tiny scale of individual particles, become visible to the naked eye. You can literally see quantum physics in action. The implications of being able to create and manipulate this exotic matter are staggering. For physicists, a BC acts like a quantum simulator, a pristine playground where they can study complex phenomena like superconductivity or the behavior of matter in the immediate aftermath of the Big Bang, all under highly controlled conditions. But the potential reaches far beyond pure research. This technology is a critical stepping stone on the path to functional quantum computers. In a BEC, the quantum information, or qubits, can be protected from the disruptive influence of the outside world for longer periods, a major hurdle in building practical quantum machines. Furthermore, the exquisite control over atoms has led to the development of atom lasers and atom interferometers. These devices use the wave-like nature of atoms to make measurements of gravity and rotation with unimaginable precision, with applications ranging from mapping underground mineral deposits to enabling ultra-precise navigation for spacecraft that venture far beyond the reach of GPS satellites. In the quest to understand the universe's extremes, we are finding that the profound cold we create here on Earth is just as illuminating as the most violent heat born in the hearts of distant stars. Far from the serene, icy moons that populate the outer solar system, Jupiter's innermost large moon, Io, presents a vision of a world in a state of perpetual, violent rebirth. While our own moon is a quiet, geologically dead sphere pocked with ancient craters, Io is a searing, colorful tapestry of active volcanoes, massive lava lakes, and enormous calderas. It holds the undisputed title as the most volcanically active body in our entire solar system, a distinction that makes even the most volatile regions of Earth seem tranquil by comparison. This isn't a world with the occasional eruption. It is a globe entirely reworked by fire, where hundreds of active volcanoes constantly spew fountains of molten rock and umbrella-shaped plumes of gas and dust that can shoot hundreds of kilometers into the sky, high enough to be seen from Earth with powerful telescopes. This incredible level of activity has a single, powerful source: the immense gravitational pull of Jupiter. Io is caught in a celestial tug of war between the giant planet on one side and its sister moons, Europa and Ganymede, on the other. Their competing gravitational forces stretch and squeeze Io's interior in a process known as tidal heating. Imagine constantly kneading a ball of clay. The friction from that motion generates heat. Now apply that concept to an entire moon, relentlessly flexing its entire silicate mantle. This friction generates a tremendous amount of internal energy, enough to melt rock on a planetary scale and power its hundreds of raging volcanoes. It's a perfect demonstration of orbital mechanics transformed into pure geothermal force. The lavas that erupt from this tortured world are not like the familiar basaltic flows we see in Hawaii. Measurements from spacecraft like Galileo have revealed that Io's lavas are incredibly hot, reaching temperatures of around 1,600 degrees Celsius or 2,900 degrees Fahrenheit. This is significantly hotter than most terrestrial lavas and is actually similar in composition and temperature to the ultramafic cometite lavas that erupted on the primordial Earth billions of years ago, when our own planet's interior was far hotter. Studying Io, therefore, is like looking back in time at our own planet's most violent and formative era, offering a unique window into the conditions that shaped all the rocky worlds in their youth. The consequence of this endless volcanic conveyor belt is that Io's surface is the youngest in the solar system, estimated to be less than 1 million years old on average. Impact craters, which record the history of most other solid bodies, simply cannot persist here. They are almost instantly buried under fresh layers of sulfurous frost and silicate lava, creating a landscape of vivid yellows, oranges, reds, and blacks, a palette painted by the complex chemistry of sulfur and its compounds at different temperatures. This constant resurfacing means that the Io we see today will be geologically unrecognizable a century from now, a dynamic and ever-changing hellscape that stands as a stunning testament to the transformative power of gravitational energy. After exploring the fiery, chaotic landscapes of Io, we arrive at a thermal story that is perhaps the most precious and delicate of all, the one that makes our very existence possible. Amidst a universe of unimaginable extremes, from near absolute zero to trillions of degrees, Earth's average surface temperature is a remarkably moderate 15 degrees Celsius or 59 degrees Fahrenheit. This isn't just a number on a chart. It represents a miraculous, narrow band of habitability in a cosmos that is overwhelmingly hostile to life as we know it. This comfortable warmth is not a simple gift from the sun. If that were the case, our planet would be a frozen wasteland with an average temperature of -18 degrees Celsius or 0 degrees Fahrenheit. The difference between the deep freeze we should experience and the temperate world we actually inhabit is a mere 33 degrees, and that life-giving difference is made by one thing: a thin, fragile blanket of gas. This blanket is our atmosphere, and its life-preserving magic is known as the natural greenhouse effect. Here's how this delicate balancing act works. Incoming energy from the sun, mostly in the form of visible light, passes through our atmosphere with relative ease and warms the planet's surface. The Earth then radiates that energy back outward, but not as visible light. It emits it as infrared radiation, which we feel as heat. This is where our atmospheric blanket performs its vital function. Certain gases in our air, like water vapor, carbon dioxide, and methane, are transparent to incoming sunlight but opaque to this outgoing infrared heat. They absorb this radiated energy and re-emit it in all directions, sending a portion of it back toward the surface. This process acts like an invisible heat recycling system, trapping just enough warmth to keep our planet from becoming an ice ball. It is a perfectly tuned natural thermostat that has maintained conditions suitable for liquid water and life for billions of years. The critical lesson here is one of profound sensitivity. A blanket that is too thin offers no protection from the cold, while a blanket that is too thick will cause dangerous overheating. For most of Earth's history, the composition of this atmospheric blanket has been regulated by natural cycles, like the slow weathering of rocks and the absorption of carbon dioxide by the oceans. However, human activities, primarily the burning of fossil fuels and widespread deforestation, are now artificially and rapidly thickening this blanket. We are pumping unprecedented amounts of extra greenhouse gases, especially carbon dioxide, into the air. Since the start of the Industrial Revolution, the concentration of CO2 in our atmosphere has skyrocketed by over 50%. This is the equivalent of adding multiple extra layers of insulation to our planetary blanket. The system's delicate balance is being disrupted, and the result is the global warming we are now experiencing. The planet's average temperature has already increased by over 1 degree Celsius, and the consequences, more intense heat waves, stronger storms, rising sea levels, and shifting ecosystems, are already unfolding around us. Earth's story teaches us that a planet's temperature is not just about its distance from a star, but is exquisitely dependent on the composition of its atmosphere. We are living through a real-time experiment that demonstrates just how precarious and precious our thermal oasis truly is. While we've seen astounding cold in natural cosmic settings like the Boomerang Nebula, achieving such extreme cold deliberately in space represents one of humanity's greatest engineering challenges, a challenge perfectly embodied by the James Webb Space Telescope. To fulfill its mission of seeing the very first stars and galaxies that blinked into existence, Webb must detect the faintest whispers of infrared light, heat radiation that has been traveling through the expanding universe for over 13.5 billion years. The problem is that any warmth from the telescope itself would completely drown out these ancient signals with its own infrared glow. It's like trying to hear a pin drop from a mile away while standing next a roaring jet engine. To hear that cosmic pin drop, Webb must become colder than the void of space itself. The first and most crucial line of defense is its magnificent tennis court-sized sun shield. This five-layered marvel of advanced materials acts like an ultimate beach umbrella, but one that creates a staggering temperature difference. The side facing the sun bakes at nearly 85 degrees Celsius, hot enough to boil water, while the shaded side, where the telescope's mirrors and instruments reside, is plunged into a permanent, deep shadow chill. This passive cooling alone brings the telescope's core temperature down to around 40 Kelvin. But for one instrument in particular, that still isn't nearly cold enough. That instrument is the mid-infrared instrument, or MIRI. To observe in the most sensitive mid-infrared wavelengths, MIRI must be colder than anything else on the observatory. Its required operating temperature is a mere 7 Kelvin, just 7 degrees above absolute zero. Passive cooling from the sunshield alone can't get it there. The heat from its own electronics and the faint warmth radiating from the rest of the telescope would keep it too warm. The solution was to give MIRI its own highly sophisticated cryocooler, a complex closed-cycle refrigeration system that had to be specially designed for the rigors of space. This cryocooler actively pumps heat away from MIRI detectors, fighting against any incoming thermal energy to maintain that incredibly fragile, ultra-cold state. The result is that MIRI is not just cold, it is one of the coldest human-made objects ever to operate in space. At 7 Kelvin, or negative 266 degrees Celsius, its detectors are chilled to a temperature where their own heat signature is virtually eliminated. This allows them to perform miracles of observation, seeing the heat glow from forming planets in dusty disks around young stars, piercing through obscuring cosmic dust clouds to witness stellar birth, and most importantly, capturing the faint red shifted light from the universe's very first galaxies. Every stunning image and revolutionary discovery from Webb's mid-infrared eye is made possible by this incredible feat of thermal engineering, a continuous, active struggle against heat itself to preserve a pocket of profound cold, all in the service of looking back in time to our cosmic origins. But this incredible technology protecting our astronauts didn't appear overnight. It was forged in the fiery crucible of early spaceflight, and one mission in particular that nearly ended in tragedy. The development of the heat shield is a story of brilliant engineering meeting a terrifying reality. During the return of John Glenn's Friendship 7 mission in 1962, Mission Control received a chilling warning from their telemetry. A sensor was indicating that the capsule's heat shield might have come loose. If that were true, the entire spacecraft would disintegrate during re-entry, incinerating John Glenn in the process. Faced with this horrifying possibility, flight controllers made a desperate decision. They ordered Glenn not to jettison the capsule's retro-rocket pack after it had been used, a standard procedure to lighten the vehicle. The thinking was that the metal straps holding the pack might help keep the heat shield in place. For 4 agonizing minutes during the peak of heating, as plasma surrounded his capsule and blocked all communications, the world held its breath, not knowing if the first American to orbit the Earth would survive. That tense silence was broken by Glenn's calm voice reporting he was through the fireball, the heat shield had held, and the retro pack had burned away as intended. That moment of sheer terror underscored the absolute criticality of the heat shield and drove decades of innovation to perfect it. Modern spacecraft use a sophisticated sacrificial system known as an ablative heat shield. The word ablative comes from the Latin for to carry away, which is precisely its function. The shield isn't designed to simply withstand the heat like a pot on a stove. It is engineered to erode in a very controlled manner. It's typically made from a composite material, often a resin filled with microscopic silica spheres or cork, creating a substance that is surprisingly light yet incredibly effective. As the superheated plasma makes contact, the outer layer of the shield doesn't melt. Instead, it undergoes a complex series of chemical reactions called pyrolyses. The resin vaporizes, the material chars and slowly flakes away, and this process does 2 miraculous things at once. First, the transformation of the solid material into gas consumes a tremendous amount of thermal energy. Second, the newly created gases are blown outwards, forming a protective boundary layer that actually pushes the hottest part of the plasma away from the spacecraft surface. It's a brilliant act of thermal deflection, using the shield's own destruction to create a protective barrier, ensuring the brutal heat never actually touches the sturdy structure of the capsule itself. Each mission carefully measures the amount of material that has been ablated away, and there is always a significant safety margin, a calculated sacrifice that guarantees the astronauts within will feel nothing more than a gentle warmth. And now we arrive at one of the most mind-bending concepts in all of physics, a phenomenon that completely upends our understanding of these cosmic monsters. We tend to think of black holes as the ultimate cosmic vacuum cleaners, swallowing everything that crosses their path, including light itself. This would suggest a place of absolute frozen stillness. Yet, according to the revolutionary work of physicist Stephen Hawking, black holes are not completely black. They actually glow with a faint theoretical heat, and in doing so, they slowly, imperceptibly evaporate over astronomical timescales. This subtle glow is known as Hawking radiation, and it implies something truly astonishing, that a black hole has a temperature. But how can something from which nothing can escape actually emit radiation? The answer lies not in the black hole's immense gravity itself, but in the bizarre and probabilistic nature of the quantum vacuum right at the very edge of its point of no return, the event horizon. Empty space, according to quantum mechanics, is not truly empty. It is a seething, bubbling foam of virtual particles, pairs of particles and antiparticles that constantly pop into and out of existence, borrowing energy from the vacuum before almost instantly annihilating each other and paying back that energy debt. This strange process happens everywhere all the time. Normally, these pairs vanish without a trace, but something extraordinary occurs when this quantum fluctuation happens right at the precipice of a black hole's event horizon. In this extreme environment, one of the virtual particles might be created just on the outside of the event horizon, while its partner is created just on the inside. The particle outside can escape into the universe, appearing as real radiation, while its trapped partner falls inward, possessing negative energy. To conserve energy, this process actually causes the black hole to lose a tiny, tiny amount of its mass. The escaped particle is the Hawking radiation, and the black hole, in effect, pays for its creation with a fraction of its own mass. It's a slow, quantum leak in the very fabric of space-time around a black hole. This leads to the most counterintuitive relationship in all of temperature science. Hawking's calculations showed that the temperature of a black hole is inversely proportional to its mass. The more massive a black hole is, the colder it is. A typical stellar mass black hole, formed from the collapse of a large star, would have an incredibly feeble temperature of around 1/1,000,000th of a degree above absolute zero. This is far, far colder than the ambient temperature of empty space, which is warmed to about 2.7 Kelvin by the cosmic microwave background. This means a large black hole is actually colder than the universe around it, so it absorbs more energy from the cosmic background radiation than it emits through Hawking radiation, causing it to grow very slowly over time. Now flip that equation. Consider a hypothetical tiny black hole, perhaps one formed in the intense density of the early universe, known as a primordial black hole. If one existed with the mass of a small asteroid, its Hawking temperature would be enormous, potentially reaching hundreds of degrees Celsius. Such a small, hot black hole would radiate away its mass at a ferocious rate. In the final seconds of its life, this evaporation would accelerate catastrophically, culminating in a tremendous burst of high-energy gamma rays, a final, explosive signature marking the complete disappearance of the black hole from the universe. While we have yet to definitively observe this evaporation, Hawking's brilliant insight gave black holes a thermodynamic character, linking the worlds of gravity, quantum mechanics, and heat in a way that continues to inspire and challenge our perception of reality itself. While we often picture Mars as a rusty, desert world that might one day feel a bit like home, the reality is a planet locked in a deep, pervasive cold that defines its every characteristic. The average temperature on Mars is a bone-chilling -63 degrees Celsius or -81 degrees Fahrenheit, but that average hides a dramatic story of extremes. At the equator on a rare warm summer day, the thermometer might briefly climb to an almost comfortable 20 degrees Celsius, comparable to a pleasant afternoon on Earth. Yet this fleeting warmth is a cruel illusion. When winter grips the polar regions, temperatures can plummet to a staggering -125 degrees Celsius, a cold so intense it makes the depths of Antarctica seem mild by comparison. This brutal thermal swing is the direct consequence of Mars's greatest weakness, its atmosphere. The Martian air is incredibly thin, with a surface pressure less than 1% of Earth's. While it is composed almost entirely of carbon dioxide, a potent greenhouse gas, there simply isn't enough of it to form a meaningful insulating blanket. On Earth, our thick atmosphere acts like a thermal sponge, absorbing heat from the sun during the day and slowly releasing it at night, smoothing out the temperature differences. On Mars, with virtually no atmosphere to perform this function, heat arrives and departs with nothing to slow it down. Any warmth from the sunlight vanishes almost instantly when the sun sets, radiating directly back out into the void of space. This leaves the surface to experience the raw, unfiltered temperature swings between day and night, and between the sun-soaked equator and the frozen poles. This extreme environment has been brought to life in an entirely new way by our robotic explorers. NASA's Perseverance rover has not only given us stunning visuals of the Martian landscape, but has also provided us with the first true soundtrack of the Red Planet. Its microphones have recorded the sounds of the Martian wind, the hum of the rover's own machinery, and even the zap of its laser as it vaporizes rock to study their composition. But these sounds are alien in a subtle, deeply fascinating way. Due to the incredibly thin, cold air, sound travels significantly slower on Mars than it does on Earth. On our planet, sound moves at about 343 meters per second. On Mars, that speed drops to only around 240 meters per second, and it varies with the temperature, which changes drastically between day and night. This means that if you are standing on Mars, a nearby sound would reach your ears noticeably later than you would expect, and higher-pitched sounds would be attenuated almost completely, leaving a landscape that would feel eerily quiet and muffled to human ears. This auditory dimension adds a profound sensory understanding to the data we receive, transforming Mars from a series of numbers and images into a tangible, if utterly inhospitable, world of silent, freezing deserts. But even the scorching surface of our own sun pales in comparison to the most infernal world we've ever discovered beyond our solar system. Meet Kelt 9b, an exoplanet so absurdly hot it literally defies the conventional definition of a planet. This gas giant orbits a star called Kelt 9, located 670 light-years away in the constellation Cygnus. The star itself is a beast, a blue-type star that is nearly twice as hot as our sun. But Kelt 9b's extreme temperature isn't just about its host star, it's about its breathtakingly intimate orbit. The planet is tidally locked and hugs its star so closely that one full orbit, its entire year, takes just 1.5 Earth days. This proximity plunges it into a perpetual, hellish day where the relentless stellar radiation superheats its permanent dayside to a jaw-dropping 4,300 degrees Celsius. That is over 7,700 degrees Fahrenheit, a temperature that doesn't just melt metal, it vaporizes it. In fact, this planetary temperature is hotter than the surface of many stars, including our own sun, and even exceeds the surface temperature of some red dwarf stars entirely. We are looking at a planet that is hotter than a star, a concept that completely shatters our celestial classifications. This unimaginable heat has profound and violent consequences for the very chemistry of the planet. On Earth, and even on hot gas giants like Jupiter, complex molecules can form. On the day side of Kelt 9b, such chemistry is impossible. The intense thermal energy bombarding the atmosphere is so great that molecules like water, carbon dioxide, or methane are immediately ripped apart. They simply cannot hold themselves together. Even individual atoms don't escape unscathed. Hydrogen molecules are torn into their constituent atoms, creating an atmosphere of dissociated atomic hydrogen. It's a world where the basic building blocks of matter as we know them are under constant assault, a place where matter exists in its most raw and broken down state due to thermal violence. This stellar onslaught doesn't just heat the planet, it is actively destroying it. The high-energy ultraviolet radiation from the host star is so intense that it is blasting the planet's atmosphere away into space. Kelt 9b is evaporating before our very eyes, leaving a magnificent, glowing tail of ionized gas trailing behind it like a colossal comet. Astronomers estimate that the planet is losing a staggering 10 million tons of its mass every second. At that rate, if the star doesn't eventually engulf it as it evolves, Kelt 9b could ultimately be stripped down to nothing more than a barren, rocky core, a ghost of its former self. This makes it a fascinating and tragic laboratory, offering us a fleeting glimpse into the final stages of a planet's life, a dramatic process of stellar evaporation that we can study in real time. Kelt 9b is the ultimate example of a planet living on the edge, a searing testament to the destructive power of a star, and a reminder that the universe can create environments so extreme they challenge our very understanding of what is possible. This literary vision of a frozen hell offers a fascinating counterpoint to the blistering scientific extremes we've been exploring, reminding us that our perception of temperature is deeply woven into our culture and psychology. While most modern depictions, heavily influenced by religious art and literature, show hell as a domain of eternal fire and burning sulfur, Dante Alighieri's 14th-century masterpiece, The Divine Comedy, presents a far more complex and chilling topography. In his meticulously structured underworld, the deepest circle, reserved for the worst sinners, those who betrayed their kin, their homeland, and their benefactors, is not a pit of flames but a vast frozen wasteland. This is the ninth circle, a desolate realm where the arch-traitor Satan himself is immobilized at the center of Lake Cocytus, encased in ice up to his chest, eternally weeping and flapping his wings to freeze the very tears that create the icy wind which keeps him and the other damned souls perpetually trapped. Scientifically, to maintain a lake of ice in such a configuration, even a supernatural one, we could infer a temperature at or below the point where water freezes. However, given the description of it being a place of absolute, soul-crushing stasis, and the fact that the ice is described as being as strong and clear as glass, we might imagine a far deeper cold. A temperature of -40 degrees Celsius, which is also -40 degrees Fahrenheit, the point where the two scales meet, feels poetically appropriate. It represents a notable extreme, a cold that is dangerously beyond our normal experience, yet it remains within a realm we can conceptually grasp, unlike the abstract billions of degrees in a supernova. It is a cold that instantly freezes exposed flesh, that makes the air painful to breathe, and that represents the absolute absence of warmth and comfort. But Dante's genius was not in calculating a thermodynamic state. It was in using temperature as a profound metaphor for the human condition. The fiery circles of upper hell punish sins of passion and lack of control, lust, gluttony, wrath. The heat represents uncontrolled emotion. In stark contrast, the frozen core of hell punishes sins of cold calculation, a deliberate and calculated turning away from human connection. The ice of Cocytus is the physical manifestation of a heart that has grown cold, devoid of love, loyalty, and empathy. The traitors are frozen in the postures of their betrayal, unable to move or interact, isolated in their icy tombs just as they isolated themselves through their treachery in life. The relentless, bitter wind that freezes the lake is generated by Satan's own futile attempts to escape, a perfect symbol of how betrayal ultimately creates the conditions of its own perpetual torment. This literary extreme of cold is in many ways more terrifying than any fire because it represents not a punishment of sensation, but a punishment of its complete and utter absence, the final, absolute withdrawal of all warmth, light, and hope. From the ultimate heat of evaporating exoplanets and the metaphorical cold of literary hell, we return to our own planet to encounter one of the most fascinating thermal paradoxes in all of science. High above our heads, beginning at about 80 kilometers altitude and stretching out into the void, lies the thermosphere. This is the highest layer of Earth's atmosphere we can meaningfully define, and it holds a record that seems to defy logic. It is, technically, the hottest part of our entire atmosphere. Temperatures here can soar to an astonishing 2,500 degrees Celsius or 4,500 degrees Fahrenheit. That is hotter than the surface of some stars and certainly hot enough to instantly vaporize any known material. Yet, if you were to somehow find yourself floating in the thermosphere, you would not feel this immense heat at all. In fact, you would freeze to death almost instantly. This incredible contradiction is the key to understanding the true nature of temperature in the vacuum of space. The resolution to this paradox lies in the critical difference between temperature and heat. Temperature is a measure of the average kinetic energy or speed of individual particles. Heat, on the other hand, is the total transfer of thermal energy from one system to another. In the thermosphere, the individual air molecules are indeed moving at tremendous velocities, having been energized by the sun's most powerful radiation. This gives them an incredibly high temperature reading. However, these molecules are almost unimaginably sparse. At this altitude, the atmosphere is a better vacuum than we can create in most laboratories on Earth. The particles are so few and far between that there simply aren't enough of them to effectively collide with and transfer that kinetic energy to another object, like a spacecraft or an astronaut. It would be like standing in a vast, empty warehouse where a single, red-hot cannonball is whizzing around at supersonic speeds. The cannonball itself is extremely hot, but the chance of it hitting you and transferring its heat is so infinitesimally small that the room would feel frigid. This is why the International Space Station, which orbits securely within the thermosphere, doesn't melt into a puddle of liquid metal. It experiences the radical cold of shadow and the intense heating of direct sunlight, but it is largely unaffected by the scorching temperature of the thin medium it travels through. This phenomenal heat is generated by a constant bombardment of high-energy solar radiation, primarily ultraviolet light and X-rays. These powerful photons from the sun smash into the sparse atoms of oxygen and nitrogen in the thermosphere, transferring immense energy that sends them flying at those incredible speeds. This process is also what creates the beautiful auroras we see at the poles. When energized particles from the solar wind are funneled by Earth's magnetic field down into the upper atmosphere, they collide with these thermospheric gases, causing them to emit light in spectacular shimmering curtains. The thermosphere is therefore not just a paradox, it is our planet's first and most vital line of defense against the sun's most dangerous emissions. It acts as a giant, diffuse shield, absorbing this harmful radiation high above our heads and converting it into this bizarre, intense heat that poses no threat to us on the surface, all while putting on one of nature's most dazzling light shows. Yet for all the cold found in the depths of space, the absolute coldest known conditions in the entire universe are not out among the stars, but right here in laboratories on Earth. While places like the Boomerang Nebula naturally cool to within a single degree of absolute zero, physicists have achieved temperatures so low they are measured in billionths of a degree above that ultimate baseline. They accomplish this not with giant cosmic refrigerators, but with exquisite control over atoms themselves, using two brilliant techniques in tandem. The first is laser cooling, where scientists precisely tune lasers to act like a kind of optical molasses. Atoms moving toward the laser light absorb the photons and are slowed down, which by definition cools them. This can bring a cloud of atoms from room temperature down to a fraction of a degree above absolute zero. But to push into the deepest cold, researchers employ a second method called evaporative cooling. They use magnetic fields to trap the pre-cooled atoms, much like a bowl holds marbles. Then, they strategically allow the most energetic, hottest atoms to escape over the sides of this magnetic trap. The remaining atoms collide with each other and re-equilibrate to a lower average energy, and therefore a lower temperature, in a process analogous to how a hot cup of coffee cools as the most energetic water molecules evaporate away. Through repeated cycles of this evaporation, matter is chilled to temperatures within a few nanokelvin of absolute zero, a realm where the bizarre rules of quantum mechanics become the dominant force. At these unimaginably cold temperatures, the very nature of matter transforms. Atoms lose their individual identities and merge into a single quantum state known as a Bose-Einstein condensate, where they behave as one coherent wave rather than separate particles. This allows scientists to create unique states of matter, like superfluids that can flow without any friction and climb the walls of their containers. These ultra-cold laboratories are far more than just record-setting facilities. They are powerful windows into the fundamental workings of the universe. By creating pristine, controllable quantum systems, researchers can simulate the complex physics of neutron stars, model the behavior of novel materials, and test theories about the very nature of space and time. In the quest to understand the cosmos's most extreme temperatures, we are finding that some of the most profound discoveries are being made not by looking outward, but by looking inward into the quantum chill we can now master here at home. But for all the incredible thermal violence we find in stars and planets, we must remember that these are the rare, bright anomalies in a cosmos dominated by something else entirely: vast, cold, and nearly perfect emptiness. If you could take a magical journey to the very center of the largest cosmic voids, the immense spaces between the great filamentary structures of the cosmic web where galaxies are mere specks of light, you would find the universe in its most fundamental state. Here, the density of matter plummets to almost nothing, often less than a single solitary atom per cubic meter. To put that emptiness into perspective, the air we breathe has about 10 quintillion atoms in that same space. This is the true vacuum of space, a void so profound it makes any vacuum we can create on Earth seem crowded and dense by comparison. In this magnificent nothingness, the very concept of temperature takes on a different meaning. Without a medium of atoms to conduct heat, temperature isn't something you feel. It's a measure of the radiation that fills the space, and that space is permeated by the faint, ancient afterglow of creation itself, the cosmic microwave background radiation. This is the cooled remnant of the universe's fiery birth, and it sets the ultimate baseline temperature for the entire cosmos at 2.7 Kelvin. If you were to place any object in the center of this great void, perfectly shielded from the distant light of all stars and galaxies, it would slowly and inevitably radiate all of its internal heat away until it reached this equilibrium temperature of 2.7 Kelvin. It would not get any colder because it would be bathed in this universal warmth. This creates the ultimate cosmic irony. The deepest voids, which feel to our intuition like they should be the coldest places imaginable, are actually warmer than the Boomerang Nebula, which actively cools itself below this universal baseline. That forgotten nebula is an incredible cosmic refrigerator, but these voids represent the steady, ambient temperature of the universe itself. This 2.7 Kelvin is the background hum of existence, the cold stillness that is the default setting for most of the volume of the cosmos. The brilliant stars, the glowing nebulae, and the warm planets are all just temporary, localized aberrations against this immense, silent, and cold backdrop. They are fleeting islands of heat and light in an ocean of darkness that will, over trillions of years, eventually reclaim that energy as the last stars flicker out and the universe continues its long, slow expansion into a state of ultimate equilibrium and silence. And finally, we arrive at the most personal and miraculous thermal fact of all, one that connects this entire cosmic journey directly back to you. Amidst a universe of unimaginable extremes, from the 5 trillion degree inferno of a quark gluon plasma to the near absolute zero of a laboratory Bose-Einstein condensate, your body maintains a constant, life-sustaining 37 degrees Celsius. This is our own personal thermal oasis, a tiny island of warmth in a cosmos that is overwhelmingly hostile to life as we know it. This seemingly mundane number is not arbitrary. It represents a precise and fragile sweet spot honed by billions of years of evolution. It is the temperature at which the incredibly complex symphony of biochemical reactions that define life, enzyme activity, protein folding, cellular respiration operates with perfect efficiency. A shift of just a few degrees in either direction can disrupt this delicate balance, turning the processes that sustain us into ones that can cause severe harm or even shut down completely. This remarkable stability is a testament to our own internal climate control system. Our bodies are masterful thermal regulators, constantly working behind the scenes to maintain this equilibrium. When we're too warm, our blood vessels dilate to radiate heat and we sweat, using evaporation to cool our skin. When we're too cold, those same vessels constrict to conserve warmth and we shiver, generating heat through rapid muscle contractions. This intricate biological dance is happening every second of every day, a silent, automatic effort to defend our precious 37 degrees against the changing world around us. But our internal regulation is only part of the story. Our ability to maintain this constant warmth is utterly dependent on the far greater planetary system that cradles us. Earth itself provides the ultimate life support system, with its atmosphere acting as a perfectly tuned insulating blanket that moderates the brutal temperature swings we see on airless worlds like Mercury. It shields us from the sun's full, searing intensity during the day and traps just enough heat to prevent a deep freeze at night. This cosmic context makes our personal warmth feel even more profound. The heat radiating from your body right now is a direct biological echo of the sunlight that was once forged in the 15 million degree core of our star, captured and converted by our planet's systems, and now sustained by your own incredible physiology. We are, each of us, a walking, talking testament to a universe capable of creating and protecting islands of exquisite order amidst a sea of chaotic extremes. It underscores the incredible fragility and breathtaking rarity of life, not as a separate entity from the cosmos, but as one of its most delicate and beautiful expressions. From the 15 million degree nuclear furnace at the sun's core to the hyper-cold laboratories on Earth where we create new states of matter just billionths of a degree above absolute zero, this journey across the thermal spectrum of the cosmos reveals a universe of stunning contrasts and profound mysteries. We've witnessed the raw, creative violence of supernovas, where temperatures spike to 100 billion Kelvin to forge the very elements that make up our world. And we felt the eerie, profound chill of the Boomerang Nebula, a natural refrigerator cooling itself below the universe's own ambient temperature. We've seen how a delicate atmospheric blanket is all that stands between our temperate oasis and the frozen silence of space, and how the vacuum between stars is not cold at all, but rather a searingly hot medium that just happens to feel freezing to any object within it. These 30 facts are far more than just a list of record-breaking numbers. They are a testament to the fundamental role temperature plays in writing the story of the universe. It is the sculptor of galaxies, the engine of stars, the architect of planetary environments, and the ultimate gatekeeper for life itself. From the quantum chill that allows for frictionless flow in superfluids to the stellar heat that tears molecules apart on distant exoplanets, temperature is the invisible hand guiding the form and function of everything we see. This exploration leaves us with a humbling perspective. The conditions we consider extreme on our planet are merely the gentle, lukewarm background of a cosmos capable of far greater ferocity and far deeper stillness. It reminds us that we exist within a miraculously narrow window of possibility, a fragile bubble of warmth sustained by a complex and delicate set of circumstances. Every time we feel the sun on our skin or shiver in the winter air, we are interacting with the same physical principles that govern the birth of stars and the evaporation of atmospheres. So, which of these incredible facts resonated most deeply with you? Was it the realization that the coldest place in the universe is right here in a lab, or the shocking truth that a planet can be hotter than a star? Share your most mind-bending moment in the comments below. We love hearing your thoughts. If you enjoyed this voyage to the edges of physics and reality, be sure to like this video and subscribe to the channel for more journeys into the amazing extremes of our existence. Until next time, keep looking